homogeneous RD, please.
Thanks very much. It's a great pleasure to speak here, and also my first time in Warsaw and in Poland in general. So as announced, my talk is about Fourier decay and absolute continuity for homogeneous self-similar measures in RD for d greater or equal to 3. I will also talk about the lower dimensions, but there I don't have anything new, but I will actually spend considerable time reviewing what is known about that. And of course, I'm happy to take questions there anytime. And it's preliminary report because it's really part of it is old, but part of it is rather new, so should be a little bit cautious. It hasn't been written in complete details. Okay. So first, let's set up the notation. What we are talking about, we're talking about probability measures in RD and the standard formula for the Fourier transform. So it's convenient to use this normalization 2 pi I, and of course this is just the usually inner product. And so the measure is called Reichmann if the Fourier transform tends to 0 at infinity. I believe that Reichmann was a Polish mathematician very during the war. So of course we know that if the measure is absolutely continuous with respect to the Lebesgue, then Riemann-Lebesgue lemma says that the Fourier transform vanishes at infinity, but the converse is false. We have many examples of singular measures which are nevertheless Reichmann measures. But often just knowing that Fourier transform goes to infinity is not enough for applications. We'd like to know some decay rates, some quantitative properties of the Fourier transform. And so here is the notation. We'll say that, well, there's power alpha decay if decay is like, and it all of course applies to psi going to infinity. I don't worry about this being close to 0. Let's assume that all these are just the norm of the vector, a gradient of 1 in norm. And so we just say dd if it's some kind of power Fourier decay, and it's also equivalent to saying that the Fourier dimension of the measure is basically the definition of the Fourier dimension, positive Fourier dimension. Sometimes we don't know or it's not true. Sometimes we can prove that there is a power Fourier decay, so then we may be happy with a power logarithm of log polynomial decay. So very briefly, I just want to say that, so these are things I'm not going to talk about, but I just wanted to put them on a slide, that recently there's been a lot of activity in this area, wide range of applications and methods used to study the Fourier decay of various measures of dynamical origin, in particular spectral gaps and hyperbolic manifolds and quantum chaos, fractal oscillator principles. So I'm not going to talk about that. So there's some names, famous names I mentioned here. Normality to arbitrary integer bases. This is closer to what I'll be talking about, but again, this is not the topic of my talk. And then geometric measure theory. So it's a little bit closer. So the book of Matila, work of published Shmerkin, I'll talk some of the applications to proving absolute continuity. And there is very, very wide range of methods that have been used. So again, this is just putting it into constant, into big field. So I'm going to talk about something much more specific. So I'm going to talk about measures which are fractal measures appearing in iterated function systems. So recall that by iterated function system, we mean, and we restrict ourselves to Euclidean space, there is a finite family of contraction mappings, at least 2. And I will count them from 0, so there are m+1 mappings, m at least 1. And well known that, there is for any iterated function systems, there is a unique non-empty compact set called the attractor, and for any positive probability vector, there is a unique Borel probability measure called stationary or invariant measure for the iterated function system, which satisfies this equation. So it can also be viewed from the point of view of Markov chains. Okay. So what is the terminology that we're going to use? We say that the iterated function system and the measure is self-affine if all the measures are really linear affine mapping. So Aj will be just vectors in Rd. Aj is linear contraction, so it has to be contraction in some norm. And we call it self-similar if the linear map is actually a similitude, which means that it's multiplication by a constant contraction coefficient between 0 and 1 and an orthogonal matrix. We say that the IFS and the measure are homogeneous if all the maps are the same. This could be applied like to self-similar, self-affine. So let me say that, of course, more appropriately, all this terminology applies to the iterated function system, because the same measure could be represented in a different way. It could be represented, for instance, both in homogeneous and non-homogeneous way, or by some other construction.
So,
as well.
maybe a question, because you mentioned the uniqueness, but you probably need to assume something about FJs to get the uniqueness, right? Of the
well, FJs are just a contraction mapping. So the uniqueness follows from basically Banach's contraction principle. So there is some kind of a space.
Okay, so maybe I don't understand what it means a contraction. Is it a strict contraction?
Yeah, strict contraction. Strict contraction. Okay. Yeah, sorry, strict contraction. Yeah, here everything is about friction. Okay. Now, just a sample of recent progress. Again, something I'm not going to talk about, but just to mention, there was huge progress in the last few years about nonlinear for nonlinear case and also for non-homogeneous self-similar case. So I start with an earlier paper by John Lee, and Thomas Solston. So for non-homogeneous self-similar iterated function systems, I guess on the line, with non-commensurate contractions, so there's some kind of Diophantine condition on the ratio of the logs, then they get polar logarithmic decay. What about power Fourier decay? Their methods don't give, so they use some Bernoulli theory. And there are many papers recently, these are all preprints in the last 2 years, so some very, very recent, obtained power Fourier decay for nonlinear iterated function systems. Again, I don't go into any details here, but just want to emphasize that what I'm going to talk about is different. So most of these results are for specific systems. We have some conditions, let's say, for nonlinearity, conditions for like being non-conjugate to a linear system, and some smoothness conditions. So under these conditions, they get power Fourier decay. But they all exclude the homogeneous linear case, which turns out to be, in some sense, more difficult, well, in certain respect, because of number theoretic connections. So number theoretic connections already kind of lurk here, but because of Diophantine conditions. We will see later what I mean by that. Okay, so now let's go to the really what I'm going to talk about. So let's start with the first general case, homogeneous self-affine measure. And again, all the maps are, so again, linear contractions, strict contractions, plus Aj are vectors, we call them vector digits. And we can always, of course, make some conjugacy and assume without loss of generality that one of the digits is 0. It's convenient. So then let's denote the homogeneous self-affine measure this way, mu AdP, so P is probability vector. Then what's special about this case is that it can be written as infinite convolution product, which is not the case for non-homogeneous case, and certainly not for nonlinear case. So basically, infinite convolution product of discrete measures sitting basically on the digits and on the images under the contraction map. And for any positive probability vector, the support is the same. It's the attractor called self-affine set, which could be explicitly written as a sum, infinite sort of sum with powers of A and Bn being the vector digits. So is there a question here that's important for what follows? And then from this, of course, one can compute the Fourier transform. So Fourier transform of a convolution is a product So we get infinite convolution product, and this can also be seen directly just from the defining equation. So you immediately get this formula, and so you basically factor out this finite exponential sum. So for j equal to 0, because a0 is 0, you get just p0, and then you have some other exponential terms, and then you are left with a similar term for a transpose applied to the backtick side. So we can continue and get this infinite convolution product, and this always converges because the norm of nth power goes to 0 exponentially fast. So this really goes to 1 exponentially fast, so the product converges uniform. Okay, so how can one approach this question? The very first step natural to do is, okay, you take a vector with large norm, and you first apply so you see what happens in that formula. You first apply this transpose linear matrix until basically you get a smaller vectors until they get it. First time you stop when you first time get into the unit ball, and then you instead of infinite product you look at the finite product. You get finite product until you get basically unit ball, and then you have something left. Okay, is this formula clear? And so basically from this you can, because the measure is probability measure, all these terms are less than or equal to 1, you estimate the whole thing as a finite product. And what happens to this finite product? Just use elementary inequality that if you have a sum of vectors, right, with okay, basically not sum of vectors, sum of complex numbers, sum of pj is equal to 1, the first term is 1, sorry, p0 times 1, and well, you basically get this inequality, elementary inequality. This way I denote the distance to the nearest integer, so it's like from Bar-Ilan approximation. Hence, for every vector, so now we restrict ourselves to smaller vectors, so you basically stop before you get into the unit ball, and then you estimate this as this finite product. And you see that there are some kind of Bar-Ilan properties lurking here, because the question is how far is this scalar product from the nearest integer.
What is theta here?
Was it eta?
Theta.
Okay, where's
On the left hand side.
Okay, I guess that, yeah, I think it's a mistake. Sorry, so this it's a leftover of some maybe formula where this was instead, yeah, it's just supposed to be this A transpose to the, yeah, so, yeah, to the, so this would be basically this psi, so the psi is, you know, like put this negative power to the, thank you.
Excuse me, I don't understand the equality in the box. So norm alpha j r mod z, it's the distance
from the nearest integer. Yeah. So so basically the point is that you can use any of this. Okay. So let me maybe show it. So basically the whole point is that if you have like p plus 1 minus p times e to the minus 2 pi alpha, right? So you have basically, so if this is 1, so this is in the same direction, otherwise we have two vectors, and you estimate how that this is smaller than, well, it turns out that I guess you put this, doesn't matter, you have some, you know, some constant times the distance from a alpha squared, just estimating the cosine, if you like, to the nearest integer. And here you can use this in terms, right? You estimate all the terms by just crudely, and you are left with only one exponential term, and this one you estimate by the. So this is what happens here. Okay. So, okay, so then the example, probably the best known example is infinite Bernoulli convolution. And this one you get by the simplest possible situation is you have on the line, you have a contraction coefficient between 0 and 1, and you have only two digits. Here actually it's common to take symmetric digits, -1, +1. And if you take equal probabilities, it's known as infinite Bernoulli convolution, denoted mu lambda. We can also use different probabilities, and then we get the biased Bernoulli convolution, denoted mu lambda. So in this case, there are many alternative definitions which have been used. In particular, you can think about random infinite sum, random series plus minus lambda to the n, where plus minus taken with equal probabilities, or probability p minus 1 minus p, and then you get a random variable for which you look at, this is a distribution of this random variable. And then Fourier transform has nice formula, it's just basically product of the cosine 2 pi lambda to the n xi. This has been studied for a long time. I'm just reporting things probably many of you know already. So Erdos did some of the early important work. His early papers showed that if lambda is a reciprocal of what's called Pizot number, then the Fourier transform does not go to 0. In particular, if lambda is 1 over an integer greater than 2. So actually for 1/2 you get just uniform measure, but for let's say 3, 1/3 you get something like a Cantor measure. But for the Cantor middle thirds Cantor measure, it's also well known that the Fourier transform does not go to 0, but it's also true for reciprocal of Pizot numbers. Pizot numbers are called also Pizot-Vidjarek-Havan numbers, algebraic integers whose all conjugates or other roots of minimal polynomial are strictly inside the unit inside the unit disk. So later, Salem actually showed that for the Reichmann property, this is if and only if. So for all the non-Pizot, you actually do have Fourier decay. Now, and this is related to the absolute continuity question, because we immediately know that if it does not go to 0, then it's not absolutely continuous. But in fact, there is a pure type law, which was even earlier, in much more general case, Justin and Wildner. So such measures, infinite convolutions, are either singular or absolutely continuous, pure type, so then it follows that it's a singular measure. But I should say that it's still an open problem whether these are the only exceptions, whether these are the only singular Bernoulli convolutions in this range from 1/2 to 2. Now, what about the decay? So Erdos Fourier decay when it's not a reciprocal Pizot. So Erdos also did important work in that direction. So in fact, this was his motivation for absolute continuity. He showed that for any compact subinterval of 0, 1, there exists an alpha, positive alpha, such that for Lebesgue almost every parameter in this compact interval, there is alpha power Fourier decay. So interestingly, that for generic lambda, topological viewpoint is still unknown. Still not known whether this is true for like second category instead of lambda, and this is not an accidental. It's not known because it's maybe, I don't know if it's true, but it's very, very difficult. It would have very strong consequences. It would imply, for instance, that for all lambda close to 1, you have absolute continuity. Because it's basically related to semi-continuity. Semi-continuity for absolute continuity goes opposite way from the dimension. So that's for dimension 1, we do know, well, now we know, of course, by value that it's true for all transcendental numbers, right? But much stronger. But if you take more general set of digits, whenever we know Lebesgue for dimension, full dimension, in Lebesgue sense, we also know for generic by lower semi-continuity, but for absolute continuity. Okay, just a remark for those who know this. Okay, now this has consequences because it's a convolution, so there is an easy formula you can break up the convolution, infinite product or a convolution into two parts. One, you drop you just go into lambda squared, right? So you have lambda squared, Bernoulli convolution, and the same lambda squared is also only shifted multiplicatively by lambda. So if you know that this one has power decay, this has power decay, you have it twice as strong power decay. And this way, Erdos showed that there is a sequence of AK tending to 1, such that the measure becomes absolutely continuous, and even with progressively smoother density, rather than the derivative, for almost all lambda in this range. By the way, this is still not being proven by any other method. This is still only using the Fourier decay, because the modern methods show absolute continuity, maybe LQ density, but they don't show smoothness of the density. Okay. Now, Kahane, later in a little note, actually he gave an exposition, which was very, very, I think, useful for many people. Observe that Erdos' argument yields actually a bit more. It yields that this is true. Of course, you no longer restrict to a compact subinterval. If you go to all 0, 1, you allow any power decay, then the exceptional set is already 0 Hausdorff dimension. So basically, you can basically see that Erdos' proof gives a dimension estimate, not really the back, 0 Lebesgue measure, but dimension, Hausdorff dimension estimate. And this became known as sort of Erdos-Kahane argument. So in summary, we know that for all lambda except zero Hausdorff dimensional set of lambda, we do have power Fourier decay. However, again, this is only for typical, for almost every. For specific ones, very few are known. It's so-called Garcia numbers, like anti-Pizot numbers, all the conjugates outside the unit circle. And they were shown by Daifeng in 1. And very recently, some other algebraic lambda, but I can't even figure out exactly what the conditions, some complicated conditions in the Mahler measure polynomial, and many conditions to be checked, but it's only for special algebraic one. And by the way, for the Garcia numbers, it's only for unbiased case. When it's biased, it's already, I think maybe Streck has already some more general. A long time, the only known ones were with for the unbiased case. Because okay, just a remark that because it's a product of cosines, so all the arguments here we're using that you basically earn something when you're not too close to an integer, but you can also earn something when you're very, very close to 0. So cosines sometimes have zeros. If you have a biased case, you have p plus 1 minus p cosine, it never comes close to 0. So then it's a little bit different situation. Okay, now what results are known for the Fourier decay? So besides Pizot number, there is a well-known class of Salem numbers, very important in many areas. So algebraic integer is a Salem number, it's kind of borderline case. There is already a conjugate equal to 1 in modulus, but there are no outside the unit disk, and then actually has strong consequences that easy algebra shows that it has to be even degree, there's a reciprocal, the others are in pairs, conjugate pairs on the unit circles. And then Kahane pointed out that decay already cannot be polynomial, and one can maybe accept logarithmic, but it's not known. So no reasonable decay rate is known. So I say reasonable because I figured out some very weak decay, log star, like how many times you iterate log until you get to a number. But so we try to work on this with Juan Marshall, but so far we don't have a result. Now, on the other hand, for some algebraic numbers, okay, if you cannot have power decay, maybe we're happy with some other quantitative, bigger quantitative, yeah, so it's known for algebraic ones. Non-Salem, it is known. So actually, there is power logarithmic. So Kirchner already figured it out in the 30s that for rationals with p not equal to 1, because p equal to 1, it's basically Pizot reciprocal, or 1/2. You have power logarithmic decay, and then with Buffetov, some time ago we showed this for algebraic integers, not Pizot or Salem. Okay. So now about applications, this had application by Pablo-Shmerkin to show absolute continuity results. Recall that there's a notion of dimension of the measure, Hausdorff dimension of the measure. So then there are two versions. There's a like low and upper Hausdorff dimension. It's infinite dimensions of full supports or subsets with positive measure. Here for dynamical matters it's usually the same, but they're exact dimensional. And so Pablo-Shmerkin had a very useful, simple but useful lemma. If you have two finite Borel measures, one of them has full dimension, full Hausdorff dimension, the other has power Fourier decay. Any power is enough, then the convolution is already absolute continuous. So dimension D is very, very close to being absolute continuous, but a little bit less, and so you have to push it. You push it with this power Fourier decay, and you get absolute continuity. And so this was his application to show that not actually for lambdas using results of Mike Hoffman, but at the same time, meaning spectacular results, they were for the dimension. So combining them with the Erdos-Kahane, so I was able to upgrade Hoffman's result to say that all lambdas from half to 1, except zero-dimensional set of exceptions, are actually absolutely continuous. Earlier it was known only for almost every, or with some dimension of exceptions, but not sharp. Okay, so now I'm still slowly getting to some new results. This is still a review survey. Now, what about general homogeneous self-similar measures? So not just Bernoulli convolutions. If you're talking the homogeneous case on the line, then the Fourier decay results absolute continuity for typical lambda and extend digit set. So they extend without much difficulty. So it's not really an issue. If you want to get sharp results, like for dimension, like, it's very non-trivial. So for instance, Hoffman's result, Various result, Ariel Rappaport extended, Rappaport and Vario extended to 3-digit set, it's already very non-trivial, not complete range. So every related to some algebraic geometric questions, it's very non-trivial, but for this kind of questions, Fourier decay and absolute continuity, it's once you know the dimension, then it's okay. Well, I guess for typical lambda, because for typical lambda, Hoffman's result does apply. It doesn't matter how many digits you have. And I should just say that much progress on absolute continuity questions has been achieved recently for specific algebraic parameters, value, Kittel, others, but it's a topic for another talk. So I'll then go to higher dimension. So let's what about R2? In R2, we assume, of course, that the attractor is not contained in a line. Then we are back into the one-dimensional case. And then there are two basic cases. One is you have a simple contraction, just identity times lambda. So then power Fourier decay for all but zero-dimensional set of lambda follows easily from the one-dimensional result. And I'll show it later. But Hoffman's two-dimensional result, Hoffman has not just two-dimensional, has high-dimensional results. But first of all, they're much harder. And second, they require linear irreducibility, meaning that the linear parts do not have a common invariant subspace. But of course, here every line is invariant. So this applies only some very special cases when there's some symmetry, additional symmetry, and the same measure can be represented also in a non-homogeneous way. Now, another case, of course, your contraction is very homogeneous, so similar. So it's either just pure contraction by lambda, or you can view it as a multiplication by complex number lambda in the complex plane, non-real lambda. So then we have a paper with Pablo-Shmerkin a while ago, basically extending the results from one-dimensional case, and there are still exceptions for complex Fizeau numbers. So complex Fizeau is the number, its conjugate, everybody else is inside the unit disk. Here we can use Hofmann's result, because when you have a rotation, it's irrational rotation, or not just not necessarily irrational, not just full rotation or half rotation. Then there are no invariant lines, so then you can apply Hofmann. Okay, and so then dimension results. So the dimension results holds, and then we get up to continuity. Okay, so now we finally get to something hopefully new. The first case is again the most simple case is when you have a contraction is just lambda times identity. So then, as the power Fourier decay follows easily. So let's see how it works. Recall the formula, and then okay. So notice that actually. Always assume that the first digit is 0. We start with a 1. And notice that we have to have at least d plus 1 digits to guarantee that it does not contain in a lower dimensional subspace. So, because after translation, we can assume that it's 0, so then because it's just multiplication by lambda, you don't increase dimension of the span by iterating, and then we can assume without loss of generality by just changing, but by linear conjugacy, that the digits are standard basis vectors. So then we have this inequality. So again, this is the same inequality. I estimate all the terms by 1, and then just leave this term. But then you see what happens is exactly the one-dimensional biased Bernoulli convolution for a corresponding. And now, because we know actually that they all have power Fourier decay for typical lambda by Erdos-Kahane, then it follows, because you can always choose because the maximal coordinate, maximal absolute coordinate, we do have, so we do have power Fourier decay. Again, I should say that for all lambda except the 0, 1-dimensional cases, kind of condition is missing here. Okay, but if we want to apply this to get absolute continuity, as I said, this is a problem with applying Hofmann's result, because in dimension 3 and higher, you always have an invariant line invariant two-dimensional subspace. However, there are some special cases where it does apply. So I guess maybe I can show one it's a funny example. Erase
The green one?
this one. It would be okay. Actually, I think it was somewhere. The web is called this way. So the fat Sierpinski tetrahedron. So like there is a fat Sierpinski. There were quite a few papers on fat Sierpinski gaskets. If you have a contraction ratio bigger than 1/2, and then so lambda greater than 1/2, so then you have overlaps, and then the question is about the measure. Of course, in the plane, so there are 3 maps. So this is R2. There are 3 maps, and then the dimension of if we call this as two-dimensional Sierpinski triangle or Sierpinski gasket S lambda 2. So then the Hausdorff dimension, we have that this is less than or equal to log 3 over log 1 over lambda. So if this upper bound is greater than 2, greater than the dimension of the space, it's called overcritical. And then, well, we expect that for typical lambda, it is going to be has positive measure. So this was indeed shown by using the absolute continuity of a uniform measure, and but how to apply it, because here the contraction mapping does have invariant lines. So So the trick is that it's already mentioned in Mike's paper that you can represent the same measure using a different IFS where you have rotation. Now we can also look at the analogous case, the 3 dimensions, so like a tetrahedron, so that's tetrahedron, and I'm not trying to draw this. Here you cannot use it using homogeneous, but each time you can use a different rotation because we can think about the invariant measure just as a geometric process, taking the unit mass and replacing by this masses, and then just looking at the weak limit. It doesn't have to be the same construction. It could be a different one at each. So it could be viewed as a invariant measure for the IFS which is not homogeneous, and using different rotation we can ensure that actually there is no common invariant subspace.
But this still requires probabilities to be uniform.
Yeah, so here it's like application is for the measure. For the Lebesgue measure it's enough because the same condition applies. But of course if you want to talk about absolute continuity for non-uniform, then it doesn't work. So then it's very restricted, very, very special. It has to be very big symmetry of the system somehow. So it's if you change it a little bit, it's already doesn't work. Okay. Now the other case is okay. So now the other case is now we so this is actually hopefully new result. Now you fix the orthogonal mapping, could be orthogonal matrix, any matrix, and you just vary the lambda contraction coefficients, but you require that the set of digits is spanning linearly, so you need to have at least d plus 1 digits, again 0 and another d sort of vectors that span the space, and then basically analogous results apply in terms of Fourier decay, that you can fix this such a set of digits, fix orthogonal mapping, then and you fix any probability vector non-trivial, that then you have power Fourier decay for all but zero-dimensional set of exceptions. And the proof is not a very difficult extension of the original Erdos-Kahane algorithm.
Excuse me, does it survive the small perturbations? For instance, if you have all not exactly orthogonal, but a little bit.
Yeah, if well, but still I want to be this linear affine homogeneous. I think it does. Yeah, I think it does. I haven't checked all the details, but I think it does. Yeah.
Another question.
Yes.
So here again to get absolute continuity.
Yeah. So this is only about Fourier decay. Only Fourier
Fourier
decay. Yeah. So here I will talk something about the absolute continuity. So if you want to apply absolute continuity, so then Hoffman results usually don't apply. So you have to apply the new results of Emilio Corso and Pablo Shmerkin. I'll get to them in a few minutes. But first I wanted to only talk about the Fourier decay. So the other result of Fourier decay is somehow, so strangely, so only for even dimension. I will explain why only for even dimension. If you take, let's see, what is that? Is it, yeah. So for even dimension, and you assume that it's not in a lower dimensional subspace, then you fix for almost every linear similitude, for every digit set. Now it's a weak assumption of the digit set, only that it is not contained in the. So in many cases it will be just 2 digits is enough, 0 and some other vector. It's already enough. So then the self-similar measure, typical self-similar measure, has a Fourier decay.
This is for all p at once, or p is fixed? Does p depend on?
Yeah, I think it does really depend. Of course, the rate will depend on p, but it's really, yeah, p doesn't matter so much. Yeah. Now, about the proof, very, very briefly, first of all, almost every orthogonal matrix in RD has distinct eigenvalues. So this is right? Having equal eigenvalues is a really restriction, dimension restriction, and it will have at most one real eigenvalue, because having two real eigenvalues means for orthogonal matrix 1 and 1 minus 1. So this is really means it's essentially equal eigenvalues. So what we do is for even D, fix all the non-real distinct eigenvalues except 1, and run a variant of Erdos-Kahane to estimate the Hausdorff dimension of bad remaining ones. So the reason it has to be done for all of the J's in turn is that basically the estimates from Erdos-Kahane, somewhat technical, can't explain this in detail, they deteriorate if the direction of the vector becomes close to that invariant subspace. And so this is also the reason why the argument does not work in the odd-dimensional case. So, because if in the odd-dimensional case, if you fix all the non-real eigenvalues, you already know the real one up to sign, right? Because it's a self-similar situation, so it will be just a contraction or minus contraction. And so then you basically cannot do anything. And basically what the argument does give, it does give Fourier power Fourier decay in every direction. But we want it uniform we want a really uniform rate, also with uniform constant. Even we can get uniform alpha, but we don't get the constant to be uniform. And so in order to apply the results of Shmerkin, so we do need some uniformity. And even though in this real eigenvector direction, power Fourier decay is known, but it's not clear how to interpolate with this direction. And just trying to, well, I'm not saying this is not true, just don't know how to prove it. Just to motivate this, so if we kind of try to use a slightly different method, instead of fixing, so here in the argument we fix all the eigenvalues except 1, and we play the Erdos-Kahane game just for the one parameter, one complex parameter. Here we could say, okay, maybe we want to just run Erdos-Kahane for the entire matrix A, or maybe the orthogonal part. But imagine, so you have an invariant line. So this is the invariant line, the real eigenvector. And so if you take a direction very, very close, then applying the matrix for a long time, you will be close to this line. So basically, the idea in Erdos-Kahane is that somehow we want to recover the matrix from, let's say, from this data. You can iterate it long time. It doesn't have to be D. It could be 2D or whatever, 100D. So you have a bunch of vectors from this. You can recover, of course, the linear matrix, but the estimates will deteriorate because it will be very small determinant. So at least it was not clear how to make this work technically. That's at least, I say it's preliminary, so for now that's the situation. Okay, so now let me finally talk about the application to absolute continuity using the recent results of Corso and Shmerkin. And so the results of, so I should say first that Pablo Shmerkin extended, or not extended, I mean, he built some very interesting theory, which was, of course, motivated, inspired by Hochman, but instead of Hausdorff dimension, you look for LQ dimension. So here, recall the notion of Q dimension. So this was the Hausdorff dimension of the measure, and it has always this natural upper bound, which is called similarity dimension. Similarity dimension of the measure is entropy of the probability vector over the Lyapunov exponent. And then there is the Q analog. For the Q analog, so how do you define the LQ dimension? So here there's how you define the Q dimension. LQ dimension can be defined in different ways. One definition is the following: you partition the space into small dyadic cubes. You take the weighted sum of Q powers, and then you get this what is called the Q spectrum, and then you divide by Q minus 1. This is called the, I guess, the lower Q dimension, because there is limit here. for q equal to 2 is known as correlation dimension, which is especially important. And it has also a symbolic analog, which is written here. So this is always an upper bound, always an upper bound. So the question is when you have an equality. And so Shmerkin had results on this for first into one-dimensional case, which has very, very strong important consequences. And recently, with Corso, they gave an extension of those results to higher dimension. Okay, so here, I guess it's a corollary of my results combined with their result, that basically when we have Fourier decay, then at least for almost every IFS we do have in the overcritical case, we do have absolute continuity with a density in LQ. Because having overcritical in using LQ dimension, actually you get LQ density, not absolute continuity, but something strong. So the first part is about absolute continuity, and here the point is that if you look at the LQ dimension, symbolic LQ dimension, and let Q go to 1, it actually converges to the symbolic dimension, and I guess it's also true, at least, forget if it's always true, or at least it's true for self-similar measure. That if you take LQ dimension of the measure and let Q go to 1, you actually get the half-order dimension. But here it's just follows. And that's why, as I say, part 2 follows by a variant of Shmerkin's lemma, which uses convolution. Now, so what about the results? So the results is fairly recent. It's a preprint from about 1 year ago. So they assume some of the similar properties. For instance, first of all, this is very, very special. This is not the most general result. This is a result which is needed for application. If you look at the homogeneous self-similar IFS, and he also does say that this is a typical situation, meaning that if you are in a even dimensional case, all the eigenvalues are non-real and different. If you are in the odd dimensional case, you should also have this property that one real, the others are different, all different eigenvalues, non-real. Sorry. And now there are two other important conditions. One is somehow stated in the paper is that you have a connected group, the closed group generated by the orthogonal map has to be connected. And I think they say, I didn't really check, I think it's clear, that this is equivalent to saying that all the alphas, these are sort of the angles corresponding to the non-real eigenvalues, have to be irrational, and all the differences also have to be irrational. In particular, they're all distinct. So then, okay, you look at this basically diagonal matrix, that's the map. And another main assumption is exponential separation. So exponential separation already appeared in Hoffman's theory. So here it has to be true for all the coordinate IFX. You actually, here, because of diagonal form, you look at in each coordinate, you look at the corresponding homogeneous self-similar IFS, and each of them has to have exponential separation condition. I'll shortly say what it means. So then we do have this dimensional result that, so this is specific, not this, under these conditions, you always have that Q dimension is the minimum of course, the dimension of the ambient space and the Q symbolic Q dimension.
Excuse me,
Yeah.
question. So for alpha I being rationally dependent, it will not prevent not be a problem here.
You mean the being connected?
Yes.
I think just rationally independent.
They are dependent.
So here, I think this is strong, right? yeah, this is from.
I mean, they can be rationally independent, is this condition satisfied?
Let's see, if the rationally dependent can it be satisfied? Yes. Right. Yeah, I'm not sure. Yeah. Not immediately clear. Yeah. Okay. So here it's Hoffman's exponential separation condition. It's a general case. We look at the homogeneous IFS. It says that it satisfies exponential separation condition if there is a sequence mj going to infinity and some epsilon such that you look at the nj stage of basically constructing the attractor or the measure, and it's a statement in the homogeneous case. So you look at two distinct words, basically two different, or you can also, another, yeah, I didn't put it here. You can also view it the following way. You go to the n stage of the construction of the measure, a discrete measure, you want the atoms to be separated by epsilon to the nj. This is actually very, very, very strong because epsilon could be arbitrarily small, so it just exists epsilon. And so that's basically the condition which has to be satisfied in every coordinate. So this condition is actually a very special case of projected exponential separation condition from their paper. There is also more general work in the framework of pleasant models, and they obtain simultaneous results from the projective measures. Okay, I still have 5 minutes, maybe. Started a few minutes later, maybe. Okay, just for
Not more than 5.
You have half an hour or so.
Oh, okay. Let's see. When do we start?
Yeah.
1 hour and a half.
Oh, okay. Oh, I can kind of. Okay, so. Oh, okay. So I was really running too fast. No, but wait. Okay. Oh no, in 5 minutes it will be 1 hour. Okay, so there's still. Oh, okay. So okay. So maybe I'll explain something on the board now. So I'm done with the slides, and we can go more slowly. Okay. So let me just to motivate. I don't think I will explain actually the proof of the Fourier decay theorem, but I want to just somehow explain the idea of the Erdos-Kahane method, going back to the very, very basics to somehow, so I just want to start with the famous open problem. Related to a Bezoar question, Bezoar number. So look at all the numbers theta greater than 1, such that there is some other number theta, such that if you take theta to the n, eta, the distance to the nearest integer goes to 0. So this is, I'm not going to write the r or z, this is distance to the nearest distance to the nearest integer. Okay, so the question is epsilon, is the set E, does it coincide with the set of Bezoar numbers? Okay, so for Bezoar numbers, it's well known that that this is and there are many known results. We know that if number is algebraic, then can only be Bezoar number, and if the convergence to 0 is fast enough, if the sum of the squares goes to 0, it's Bezoar number. These are original results of Bezoar, but still we don't know. This is still an open question. But what Salem pointed out that is that this set is countable. So if there are some transcendental numbers, at least we know that it's countable. And how do we see that? Well, you write theta to the n theta equals to kn plus epsilon n. Kn is the nearest integer, epsilon n is the distance, well, which remains error. Then we do it for n plus 1 as well, and so on. And so from this, we see that theta is approximately equal to kn plus 1 over kn. And in fact, it is clear, because epsilon n is less than 1/2, it's clear that theta is actually a limit of the ratio kn plus 1 over kn. So if we know the sequence of integers kn, then we know theta as a limit. Now, notice that also, if several epsilons in a row are small, you can actually recover kn plus 2 from kn plus 1 and kn. So this is from this also writing this for n plus 2, you see that kn plus 2 is approximately equal to kn plus 1 squared over kn. And so there is a very simple lemma, that if you fix in advance some compact interval, now we are okay, so here theta is greater than 1 and also eta is greater than 1. And you see somehow it's very, very close to what was before, just a very, very specific situation. So if you fix compact intervals from 1 to infinity, then there exists a positive number rho, which is very easy to write explicitly, such that if maximum of epsilon n plus 1, which would be negative, epsilon n plus 2 is less than rho, then indeed kn plus 2 is determined by them, then kn plus 2 is the nearest integer to this number. Okay? So this is a very standard trick sort of in Diophantine approximation, because it has to be and so then you actually conclude the Salem's claim, proof of Salem's claim very easily. Of course, it's enough to show this for right. So if there exists such a thing, it's enough to do it for any compact interval. You have countable such possible acceptance, and so if epsilon n tends to 0, then this is true for some point on. So then if epsilon goes to 0, then eta is determined by some initial part of the sequence k, k1 up to kn0. So basically, there is a map, right, from a set of finite integer sequences to thetas. And so therefore, we get that this is counting. So I think Erdos was motivated by this, was inspired by this, and say, okay, in general, if it doesn't go to 0, but in order to get, let's say, power Fourier decay, it's enough to have that epsilon n's are not too small for a positive density number of n's. Okay, so basically for a very rare sequence of epsilons. So that means that most of the cases, like suppose that it's not true. You want to estimate the bad set, the dimension of bad set at some scale, so that up to certain point n and big N, you very rarely, less than 1% of the times you see epsilon less than 1,000. Okay, so then you can estimate, basically combinatorial estimate, how many possibilities you have, because most of the times you have kns determined by the previous ones, and this does give you some bounds. So it always gives you some bounds. So you basically have a good covering for the bad set at scale n. So this is actually the way the Erdos, and this was very well explained by Kahane. So you actually get the dimension estimate, get some kind of lim subset. The bad set is lim subset, you get an estimate of this dimension. And basically all the variants of Erdos-Kahane play the same game. So what changes is that you have to you always start with writing up some such thing. Of course, it could be a vector. Kn epsilon could be vectors, and you play this game. You try to recover. So you try to recover, instead of theta it will be a matrix, instead of eta it will be a vector, and you try to get some formulas which could be then made into this sort of arguments. Of course, each time it's a little bit different, but that's like somehow underlying idea which worked, which was in this situation. Okay, so this was one thing which I wanted to explain, and okay, the other thing maybe I'm not going to take another all that. Oh, let's see. So so maybe just to explain this Shmerkin's lemma, it also explains somehow where the somehow how this convolution works. So original Shmerkin's lemma so this is not new, so let's explain the Shmerkin's lemma was both for Hausdorff dimension and for the correlation dimension. So recall that the correlation dimension can be defined in various ways, in particular as limit log so basically this is correlation, right? You integrate the measure of the ball relative to the measure itself, and you divide by log r, and you take limit as r goes to 0. This is one of the formulas for the correlation dimension, not the formula which I used for with the weighted sum. So it's another formula which is equivalent, and it's known that this can be also represented using energy. So supremum of S such that S energy is finite. S energy is double integral divided by x minus y to the s, which can also be expressed using the Fourier transform. So this is explained very well in much of this book. So basically, using the applying the Fourier transform using, I guess here it has to be done as with generalized functions. Okay, so you have this. So this is another formula for the same energy. Okay, so basically
for S between 0 and 1, it doesn't
What
work
then?
for S, the equality with the Fourier transform. For S greater than 1.
Yeah, okay, yeah, S has to be greater than 1, exactly, yeah. It's only for S greater than 1.
But it doesn't matter for the...
Yeah, for the application, we only do it for S greater than 1, yes. Okay.
So the technical question, can I now
Yeah.
close the sharing and
Yeah,
so
sure.
we have more blackboard.
Okay, sure.
Boris, it is smaller than 1. S.
S smaller than 1?
Smaller than 1. S is smaller. You wrote in the second line at the end of the second line.
Yes.
It is smaller than 1.
Okay. Here smaller than 1. Okay, so I guess the point was that, right, that this formula applies, okay, no, but
It's smaller than
you mean for the Q dimension, but this is for Q equal to 2 actually, right? So there is analogous formula for any Q, but only for Q greater than 1. So analog of this, I think, it was by
So if we are on the line, then S smaller than 1. If we are on
right.
the line,
Okay,
then
here we are in R. Okay, here D is equal to 1. Here
okay,
it's all
then S smaller than 1.
yes, you're right. Yes, you're right. Okay. So then lemma. So Shmerkin's lemma from 2014 actually has two parts. The first part that suppose that one measure mu is has some powerful decay, and another measure mu has the property that the correlation dimension is equal to 1. It's maximal possible on the line. These are measures on the line. So then the convolution of these measures is absolutely continuous with respect to Lebesgue, and the radon negative derivative, the density is L2 with L2 density. And then the second part is what I mentioned before, that if again mu has powerful unity, and now the Hausdorff dimension of mu is equal to 1, so then you simply say that you can simply only say that the convolution is absolutely continuous. Okay. Now, so what does it mean that you have Fourier decay? That means that there's some power Fourier decay, and so T is positive, and I don't worry about psi small. This is everywhere for psi sufficiently large. So then we can take S, right there, 1 minus T over 2, and then we get that integral of psi minus T over 2 times mu hat psi squared psi, right? So okay, so then we know that this is finite, right? Okay, let's see, right? So we know that, yeah, because we know the dimension is 1, so that means that for every number less than 1, right? No, sorry. No, yeah, so there exists a number. Yeah, there exists a number. Okay, there exists. Yeah, there exists. No, it's okay. Yeah, because sorry. Right. Yeah, so this is true for every number. So we know that there is some power of decay. We can put this t, and so what we obtain is that by convolution, taking convolution, we obtain that now putting the positive power. Right, so this is already finite. So what this implies is that this is an L2 by Plancherel formula, right? So first of all, this is growing. So if we for large psi we can just ignore this, and this already says that the Fourier transform is an L2. So therefore, by Plancherel we know that the convolution is absolutely continuous with L2 density, but actually it even has some fractional derivative, depending on it. So that is the proof of the first part, just a couple lines. It's very, very simple. And the second part follows by Yegorov, because it's known that you can write by Yegorov's theorem, you can express the Hausdorff dimension that, like for almost all points with respect to the measure, you have corresponding decay. So you can basically throw away, by Egorov can throw away a set of arbitrarily small measure, and you get a measure restricted to a set of almost full measure, which is actually has uniform decay, and then from dimension 1 it will follow that it has correlation dimension 1. So and for that measure we do have absolute continuity. So then it follows that this measure itself is absolutely continuous. But of course, you cannot say anything about the density of this measure, because you really do this approximation up to arbitrarily small measure. So that's basically the underlying thing. I think I'll stop here. Thank you.
Thank you. Are there questions? I have a question. So, back to Bernoulli convolutions. So, for absolute continuity, there is this conjecture that the Poisson numbers are the only exceptions to absolute continuity, right? Is there a similar conjecture for exceptions to the power Fourier decay? We know that it's a larger set than just Poisson, right? Because I think
So Salem definitely doesn't have power Fourier decay.
does not have power Fourier.
Yeah, that's known. Yeah, so I don't know. I don't know. It's,
you don't have some algebraic intuition.
yes, of course. It's always here. It was only about this typical. As I mentioned, there are different results for specific ones and for almost every. Typical, often we get stronger results. So it's not clear, because actually compared with Bernoulli convolutions, I think it's even fewer numbers are known to have power Fourier decay.
Then absolute continuity.
Compared to absolute continuity, there are some algebraic numbers now, largest set of algebraic numbers for which it's known that there's absolute continuity by Vario and Kittel also. Because for other, basically it's just one method to get absolute continuity. There are other methods, and so for some methods it's not. So what happens actually for any Bernoulli convolution is that for most it's only like very rare frequencies where you don't have because it's can actually right here that actually for all lambda between 0 and 1, like typically or on average there is power Fourier decay. Actually, very specific Fourier decay. Actually, it does follow from, let's say, uniform distribution, because
so typically with respect to the frequencies.
well, yeah, I mean typically like for typical initial like for almost certainly like for almost every eta bigger than 1, if you look at stated n eta, it will be uniformly distributed, right? It's uniformly it's uniformly distributed mod 1. So you immediately get some kind of power Fourier decay so if you get some specific number for almost every, you'll get so basically the lim sup and lim behavior is very different. And also there are works by Fuji with some other people which show that if you throw away, later by Shmerkin in more generality, Mascara I think, that if you throw away some small number of frequencies, actually you do have power Fourier decay. So it's kind of like very rare places where you, even for Poisson numbers, doesn't matter. For any, there are all numbers theoretic questions somehow disappear. So there's like upper bound, which could be bad, and lower bound is always kind of nice and so for some purposes it's not.
And one more question. So the non-homogeneous case in dimension 3 and higher. What is known about Fourier decay then? Is it?
No, I haven't thought about it.
Okay.
Yeah, in general, I didn't really talk much about non-homogeneous
Right.
case. Non-homogeneous case, there are some results using this decomposition integral, first with Shmerkin Salieti, then with Adam. We did it in the plane, but high dimensions it's not known. Fourier, I expect that
It should work.
maybe it should work, but you know, I have a paper actually, which I didn't mention, in the one-dimensional case that for all but I think half the dimension zero set of parameters, like different parameters, sets of parameters, you do have power Fourier decay. It's a variant of Erdos-Kahane, but it's more complicated. So it's
But this is again, this is in dimension.
only dimension one. It was only in dimension one. Maybe it works in high dimensions. It was already hard enough. So it's a significantly more difficult version of Erdos-Kahane somehow. So there are some different techniques for non-homogeneous case used by other people using renewal theory. So you kind of have to play with the distribution. Yeah.
Okay, thank you. Maybe there are some questions online.
Yes, Paulina asking whether similar results are established for the rosy gasket and legged gasket reference.
Which gasket?
Rosy gasket, legged gasket, and friends.
I am not familiar with that. That's rosy gasket is very non-linear. So I was only talking about the linear. What was the other gasket?
Legged.
I'm not sure. Yeah, but I think it's also non-linear. Some kind of but there was this very recent results in parabolic case, which I only saw like announcement. I didn't really even see the details of that paper.
So if there are no more questions, let's thank Boris again. Thank you.
So this is the last regular seminar this year. And I'm assistant, but we have several